Greetings viewers, this video will go through Cambridge A-Level Further Mathematics Syllabus Code 9231. This is Further Pure Paper 2, Variant 4 from the May-June 2025 series. Attempt question 3 now. The previous questions have been done and uploaded into the playlist. This question is giving us a second order differential equation which is not homogeneous and giving us some boundary conditions also. So first, it's not homogeneous, so we have to, or you can recall that the solution will consist of a homogeneous part and a non-homogeneous part. So let's first take a look at the homogeneous part. For the homogeneous solution, we just take the second order differential equation and then we equate it to 0. So we discount, or we do not consider this function at the right hand side here. And of course, you should know that the solution to this type of equation, we have to assume a homogeneous solution in the form of e to the rx, right? So the first derivative that will give us re to the rx, and then the second derivative gives us r squared e to the rx. Okay, so we substitute this back into the differential equation. We get this. So each of the term have a common term of the exponential. So we can factor this out and we are left with a quadratic in terms of r, which is we call as an auxiliary equation. So we should know that e to the, or the exponential function, they will never equal to 0. It will tend to 0, it will go very close to 0, but it will never actually equal to 0. So that does not give us any solution. The only solution is from this auxiliary equation, where we need to use the quadratic formula here because it's not factorable. So the quadratic formula, yeah. So you notice that the solution to this auxiliary equation is a complex number. You need to recall, unfortunately, this is something that we need to memorize and recall. For a complex solution for the auxiliary equation in this form, lambda plus minus omega I, the solution, the homogeneous solution, it will be given in this form: e to the lambda x multiplied by c1 cosine x, cosine omega x, plus another arbitrary constant c2 sine of omega x. Okay, so this is the form of the solution when the roots are complex. So in this case, our lambda is -2, so we just substitute that into the equation and give me more space. So the homogeneous part of the solution, e to the -2x, and a constant cosine of x plus another constant sine of x. Okay, so that's the homogeneous part done. Now we go for the non-homogeneous part, or which we need to use the undetermined coefficients method. The method of undetermined coefficients, we first need to look at whatever the function is on the right hand side of the second order ODE, and we need to assume a function similar to that form. In this case, it's a exponential function, so we need to assume a solution yp of x, particular solution, to be a constant k multiplied by e to the unknown power gamma x. So we need to, again, with similarly for to the previous one, we need to find the first derivative, gamma k e to the gamma x, then the second derivative, so we get gamma square k e to the gamma x. Alright, then we substitute back into the original differential equation where we include the right hand side this time. Up till here, we can notice again all three terms, they will have the same k e to the gamma x is as a common term, so we factor it out again, and we're left with a quadratic expression, and equals to 13e to the 3x. So what we're doing here is we will just compare the coefficients, right? So we have a 3 and the power which is same as gamma. So gamma from this relation, gamma must be 3. Okay, gamma must be 3. And secondly, we have the coefficient in front of the exponential term. So whatever that is in front here must be equal to 13 also. So we write gamma 4 gamma plus 5 multiplied by k must be equal to 13. So using our values of gamma, we substitute in the equation. For k, we should be able to get 1 over 6. No, not 1 over 6. 1 over 2. Yeah, 3 squared, 9 plus 12. So 21, 26. Okay, k is 1 over 2. Okay, so our therefore the particular solution gives us half of e to the wait, k is the one in front, right? Yeah, half e to the 3x. Okay, so this is our particular solution. So the now all we need to do is write the complete solution, general solution of y of x, using the principle of superposition. The solution will be the sum of the homogeneous and the particular parts. So we just add it, e to the negative 2x c1 cosine x plus c2 sine x and half of e to the 3x. Okay, up to here, this is only the general solution because we have two unknown coefficients here that we still need to find, c1 and c2, we call as the arbitrary constants. Then given these initial conditions here, x equals to 0, y equals to 1, and dy dx equals to 0. So we can use that information to solve for these two coefficients. So first, let's do the part where y0 is 1. Okay, since everything, we have the y function already, so we just use this one. What I'm highlighting in blue will go to cancel to 0, and everything I'm highlighting in green will cancel to 1. Okay, exponential to 0, that is a 1, sine 0, that is a 0, cosine 0, that is 1. So we yield c1 equals to negative half. Okay, so that's the first equation, or the first constant found. Now we need to use the second condition, dy dx. Or first we need to find dy dx first. Okay, so using this, to find the derivative, you need to use the product rule, because e to the 2x multiplied by this function, that is the product. So first I'm differentiate the exponential term, and I'll leave the trigonometric functions. Then I will leave the exponential and I differentiate the trigonometric functions. So 1 over 2 e to the 3x, that just becomes 3 over 2 e to the 3x. 3 over 2. Then we know that dy dx evaluated when x equals 0, that is 0. So yeah, let's substitute all the values. And once again, what I'm going to cancel in green, that will get 1. All the exponential goes to 1, and cosines go to 1. And the ones in blue, sine, goes to 0. Oh, I have an error in my computation here. C1 is supposed... Okay, 1 minus half, that is positive half, not negative half. Okay, so this one, take note here. C1 is positive half. And yeah, therefore C2 you should be able to get a negative half. After this is all the constants that we have found already. Now all we need to do is rewrite our final particular solution, e to the negative 2x, where c1 is half cosine x minus half sine x, add together with half of e to the 3x. Yeah, so this is That's the final solution, the final particular solution of the second order differential equation. Thank you for watching.